Hi everyone, welcome to the regression analysis lecture. This is one of the subjects in the Statistical Science Study Program, University of Indonesia. So for this session, we will be elaborating about multicollinearity in linear regression. So then it consists of like what is the multicollinearity and the consequence of having multicollinearity in our model, and then how to detect multicollinearity and remedy for this problem. Okay, so we start with what is multicollinearity. So multicollinearity is that the problem where we have here, for example, in multiple regression, we have x1, x2 all the way to xp. We have p explanatory variables, and then while we want to have like a strong correlation between each of the x's here to the y, to the response, we don't want to have the correlation between x's. Okay, so that's the problem of multicollinearity. That is where we have like a correlation between the covariates. Okay, so if the predictors are correlated, no need to be all of them, but just like minimum two of them are having correlation, then there's the problem of multicollinearity. Okay, so now we know that what is multicollinearity problem, then what is the consequence of having that problem in our model. Okay, now let's have a look at this. Okay, we have this model expected y equals to the combination of x1 to xp through a linear function in here, linear function of beta. Then we can just rewrite it in the form of matrix vector like this. Okay, we have matrix y equals to x and beta. Okay, I think in other videos I've already explained what is the entries in y, the entries in x, and entries in beta. Okay, now using ordinary least squares, we can just try to, or we want to estimate the beta here. So then because x can be, if we have a sample size of n, then the matrix x will be of the size n row and p plus 1 column. So we can't just have like x transpose x here to get the beta. So we need to make it like a square matrix first, and thus we multiply by the transpose, okay, on the left. And we do the same thing for the left hand side here. Okay, so we have x transpose y equals to x transpose x multiplied by beta. And then now we just think of x transpose x as one quantity itself, because actually what we want to have here is the beta. Okay, so then to be able to get beta, then we just need to eliminate the x transpose x, and then how we do that is that by multiplying by its inverse from the left. And also we do the same thing here for the left hand side. So this one, x transpose x inverse multiplied by the x transpose x, it will give us an identity matrix. An identity matrix multiplied by the beta is just the beta itself. Okay, so we get the solution here. The estimated beta coefficient for the regression is given by x transpose x inverse multiplied by the x transpose y. Okay, so why do we go all the way here just to explain the multicollinearity? Because then we can see here, okay, I'll just give you an example. Okay, a matrix. Let's say our matrix data consists of 3 observations with 2 two variables. Okay, just ignore first the factor of ones like we have in here. Okay, so for example, the first x, let's say x1, consists of the value of c1, c2, c3, and x2 is actually just double of that x1. So there's like a perfect correlation here between x1 and x2. Okay, so what will happen here is that let's look at the transpose. It's like that. and then we try to find the x transpose x, it gives us something like this. And then so if we multiply the first column, the first row and the first column, we get this c1 squared plus c2 squared and so on. And then for the first row second column, first row second column, you get this result. And then the second row first column, second row first column, you get this. And then the last one, we get this. Okay, so what we can see from here is that actually we can see that column 1 here and column 2, there's the relationship between these two columns. That is column 1 or column 2 is twice of column 1. Or if we look at the row, we can say that row 2 here is the double of row 1. So what's the consequence in that? Okay, go back to here, our beta is x transpose x inverse. X transpose x inverse, we can just do the calculation by 1 on the determinant of the x transpose x multiplied by its adjoint, by the adjoint. Okay, so now we have the problem here. Okay, for x transpose x like this, we have that, remember your course in linear algebra, that is when one column is linear combination of the other columns, and here is a multiplication of other columns, or one row is kind of like a linear combination of the other rows, then you will have that the x transpose x, the determinant of that matrix will be 0. Okay, so for here the determinant is exactly 0 because this is kind of like, we can see here this is a perfect multiplication. But if it is not really perfect, I mean that probably just, okay, this is 1.9 C2, this is 2.1, this is 1.5 C3, something like that, but there's showing like a strong correlation, then we can say that the determinant is close to 0. Okay, so the problem in here, when we have that correlation between each of the variables, some of the variables in the predictors here, then we have the problem with the determinant here close to 0. Okay, so what's the problem with the determinant close to 0? It means that just small change in x, okay, in each of the x, small change in x will have an effect on, there's a change in the determinant of the x transpose x. Okay, but then even a small change in the determinant of the x transpose x, because it is down here at the denominator, then it will give a high difference in the estimated beta. Okay, so here we can see, and this, the determinant here, in the case there is a correlation between x, okay, around 0, just small change can be like, from 0.001 to 0.002 or to minus 0.001, right? It's a really small change in here, but the effect is very large in the beta. So for example, like this, let's say the determinant of x transpose x is 0.001. Then we have that beta is that given by this formula, 1 over the determinant multiplied by the adjoint and multiplied by the x transpose x. Let's say, this thing is just a constant b, okay? Just to simplify our calculation. And let's say, so we have here the estimated beta. Okay, this is just considered for one beta. We have b of 1 on 1,000 because 0.001 is 1 on 1,000, right? So here we get that the estimated beta is 1,000 b, where b is some value determined by this expression. Now, if we put like a change a little bit on the x, kind of like, we get more data, and then, there is variation in the data, so there's like some changes in the x, and then it will give some changes in this x transpose x, And so let's say it affects the determinant, so it changes from 0.001 to 0.002. If you look around this, there's just a really small change, right? Okay, for the determinant around 0. So we have the beta is actually 500p, and that's kind of like, a very big change in the estimated beta. For example, previously, let's say b equals 1. So you get that the estimated beta is 1000, so you can just do interpretation like this one, or x1 increased by 1 unit, the tendency for y to be increases by 1000 units, like that. But then when there is small change, like maybe you add one or two more data points, there are small changes in x and small changes in the determinant of x transpose x, but then the estimated beta now, this changes significantly to 500 from our previous scenario. So previously we say that x1 increased by 1 unit, the tendency for y to increase is 1000. But now, by just adding one or two data points, we get so big difference. We say that x1 changing by 1 unit, then the expected y changes by 500 units, which is like, wow, that's a big difference. So what actually you want to say? So is the effect of x1 is 1000 or 500, something like that? We can't really decide. Okay, or probably something else, like, okay, because around 0 it can cross the boundary to plus or minus, like quite what is it, easily. So let's say that, okay, the x transpose x, the determinant is minus 0.001. Okay, it should be just two zeros in here. So we have that our estimated value is minus 1000b. Just like, previously you say that increasing of 1 unit in x1, there's a tendency for y to increase by 1000 points, but then later you say that increasing of 1 unit in x1, there's a tendency of decrement in y by 1000 unit. So it means that your story is not really consistent, okay? So that's the problem when having the multicollinearity. Because simply speaking, correlation between x means in your matrix data here, one column is kind of like a combination of the other column. The consequence is that the determinant of x transpose x close to 0, which means that a small changes in x, big changes in the estimated beta value, which means that what you're saying in there is like not really consistent. Okay, so for example like this, we have, okay, something like this. Let's say we have two variables, x1 and x2, and there's like correlation between x1 and x2. So previously, okay, something like this, but then I add one more data point, and then now it changes a lot. Okay, so why we say that, oh, the increase is 500, for example. Now we say the increase is by 1000. So our story is not really consistent. Even sometimes we can say that sometimes the beta is negative. Some other times it's positive for the same data points. Okay, it all could happen because of the problem that we just explained here. Okay, so to conclude that, we say that partial interpretation of beta is not recommended when multicollinearity exists. Okay, because the story is not consistent. So we can't just do interpretation for each of the beta here. Okay, because it will just lead us to some inconsistent stories. Okay. So that's why we say that we can't do the interpretation for each beta when the multicollinearity exists. But what about doing prediction? Let's see for this illustration. Let's say that we have on the left side is for the case scenario when there is a multicollinearity problem. On the right side is when there is no multicollinearity. Okay, let's say we have explanatory variables x1 and x2. And then we have another explanatory variable, that is x2. And because of multicollinearity, which means that x1 and x2 are correlated, by correlated, in plain speaking, we say that they share the same information. So there is like a redundancy in the information that is given by x1 and x2. While no multicollinearity means like x1 and x2, they are just independent, no sharing information between them. Okay. And then, so let's say here the purple one in here is the common information shared by x1 and x2. So the blue part here is only explained by x1, that is cannot be explained by x2. The light purple here is only explained by x2, cannot be explained by x1. But here the shared information, common information here is that can be explained by both x1 and x2. While for the case with no multicollinearity, we can't really do something like that. Okay, now go to the interpretation of the partial effect of each of the covariates. So we say that, for example, beta 1 is actually the contribution of x1 in explaining the response after contribution for all other variables are considered in the model, which means that beta 1 is only telling the story about this blue line. Okay, while for the case where there's no multicollinearity, the same thing actually. Beta 1 is like telling the story about the contribution for of x1 to the response variable after all other contributions from other variables already considered in the model. But since there is no overlapping information, so then beta 1 is just like this, the whole story from x1. In multicollinearity, only this blue part here. Similar with beta 2 here, beta 2 for the multicollinearity case, again the interpretation is actually the same with the one when there is no multicollinearity, that is the contribution of x2 in explaining y. After considering all other contributions from other variables, but since here there's an overlapping information from x1 and x2, so the one that is explained by x2 only is just this part, the light purple here, while when there is no multicollinearity is the whole part here. Okay, so that's why what we can say that partial interpretation, or interpreting each other contribution of each variable in the case of multicollinearity is not recommended. Okay, no multicollinearity is fine. However, if you want to do the prediction, remember the prediction is that predicting y from all informations that we might get. So here is from all the x1 and x2, so still the whole story is the same. Okay, no matter what happened in here, but I will just take the union of information from x1 and x2. So it doesn't matter whether beta 1 works properly or not, but in the end all other things are put in here, so it's okay for the prediction. The same with here. Okay, so in other words we can say that, okay, while we can't do partial interpretation for each of the contribution for the explanatory variables, but still we can do the prediction for the case of multicollinearity, because the reason is that for the prediction you take the whole thing. Okay, and the whole thing, we don't care about what happened inside here, we just take at the union. Okay, so that's for explanation of the consequence of having multicollinearity in our model. So let's see at some illustration of the multicollinearity. I've generated some data here, and then let's see Okay, one way to detect the multicollinearity is that because from the definition, multicollinearity exists when you have correlation between the explanatory variables. So that's why we just try to produce, the pairwise correlation here between among the variables. And actually, we can see here x1 and x2. It has really high correlation. 0.99, x1 and x3 minus 0.48, and x1 and x4 is not really that correlated. Okay, it's still feasible for us to have this kind of correlation matrix, but it would be nice if we can just get a visualization. Usually is kind of like what is it um, much better, okay, quicker information that we get from the visualization. So in here we can see that, okay, the darker on the blue, it means that strong correlation. The same thing in here, light color means like low correlation. So in here that we can see x1 and x2, the correlation is really high, almost the same color with x1 and x1. Of course in here is the perfect correlation because it's with itself. Okay, so here we can see x1 and x2 high correlated, x1 and y high correlation. That's good because it means that x1 is really good explanatory for y. x2 and y is high correlated, and that's also good because it means x2 and y, x2 is a good explanatory for y. Okay, x3 high correlated, yeah, quite good correlation with y. That's good. So actually we want the one that in this column is to be high because it means that all these variables are good explanatory for y. But we want actually for a good regression, we want to have like, the one in here is should be low correlated to avoid the multicollinearity problem. Okay, but in here we see that we have a problem with the correlation of x1 and x2. That's really bad, and x1 and x3 also kind of like high correlation. We can see x1 and x3 is at minus 0.48. Okay, so there's a strong indication here. Although here we have x1 and x4 or x3 and x4, the correlation is kind of like small, but still because we have x1 and x2 is highly correlated, so we can say we have a multicollinearity problem here. Okay, so that's how we detect the multicollinearity. And so one way to avoid that problem is that we can see here, although x2 is a good predictor for y, but since x1 and x2 are really highly correlated, so probably we can just exclude either one of them, either excluding x1 or excluding x2. And actually it doesn't it's not a problem because x1 and x2 share almost the same information, right? So we don't need them both in the model. So which one should be excluded, x1 or x2? So we might just consider the one that's not having high correlation with other variables. So for example, like this, x1 and x3 and x4, oh yeah, just the same. x2 and x3 and x4 also kind of like the same pattern. We see here the first line and the first row and the second row here. So probably you can just choose whichever, just exclude either x1 or x2. Okay, and then after that we can just try to um, kind of like check again whether our model is good enough or not. However, you don't have to exclude them, either x1 or x2, if you just want to do the prediction. Okay, however, if you want to do like interpretation of each of the axes in your model, then uh, multicollinearity problem really messing up everything, so it is not recommended. Okay, so I think that's all what we can say about the multicollinearity. Thank you.